On July 1st, 7 miles of 7 billion-year-old ice came screaming into our solar system at 130,000 miles per hour. This isn't just another space rock. This is water ice older than Earth itself, preserved in the cosmic deep freeze since before our sun was even born. We're about to witness the coma of an ancient comet, examine ice from alien star systems, and decode messages written in starlight from the early galaxy. But we have just months before it vanishes forever behind our sun. Hit that like button and subscribe, because you won't want to miss this cosmic time capsule. Prepare yourselves. We begin. The telescope in Chile was doing what it does every clear night when everything changed forever. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System was scanning the southern sky for dangerous space rocks. Just another routine survey of the cosmic neighborhood. The automated system captured thousands of images, processing them through algorithms designed to spot anything moving against the background stars. Most nights, it finds asteroids, sometimes comets. This night, it found something that shouldn't exist. The object appeared as a faint dot, barely visible against the dense star fields near the galactic center, like finding a single firefly in a stadium full of Christmas lights. What made astronomers stop and stare wasn't how it looked. It was how it moved. This thing was racing across the sky, faster than anything they'd seen before, covering distances that would take normal solar system objects weeks to cross. The initial observations showed speeds of over 60 kilometers per second relative to our sun. That's fast enough to circle Earth in just 11 minutes. Numbers like this don't happen by accident. Objects moving this fast can only mean one thing: they're not from around here. Within hours, observatories around the world were turning their instruments toward this mysterious visitor. The Zwicky Transient Facility in California found it in their archives. The Canada-France-Hawaii telescope spotted its faint glow. Each new observation confirmed what astronomers were starting to suspect but hardly dared to believe. This wasn't just another asteroid tumbling through space. The trajectory calculations showed something extraordinary. The object was following what scientists call a hyperbolic orbit, meaning it would never loop back around our sun. It was passing through our solar system like a cosmic tourist, here for a brief visit before continuing its journey into the infinite dark. The Discovery team initially gave it a temporary designation, 11PLA-3Z, a cryptic code name for what would soon become one of the most important astronomical discoveries of the decade. As more telescopes joined the hunt, the evidence became undeniable. This object had traveled between the stars for millions, possibly billions of years before stumbling into our neighborhood. The Minor Planet Center, the official authority for cataloging cosmic visitors, needed just 24 hours to make it official. On July 2nd, they announced the confirmation. Humanity had found its third known interstellar object. The designation changed from that cryptic code to something far more significant. 3. Atlas. The 3, marking it as the third interstellar visitor we'd ever detected. Think about that for a moment. In all of human history, we've confirmed exactly 3 objects that originated beyond our solar system. This cosmic messenger joined the legendary ranks of Oumuamua and Borisov. Yet even among these rare visitors, this new arrival would prove to be different. Special. Ancient. The discovery was just the beginning of the story. But what the telescopes revealed next would challenge everything we thought we knew about the age and composition of interstellar space. This cosmic visitor almost slipped through our fingers completely unnoticed. Amateur astronomer Sam Dean was digging through telescope archives when he made a startling discovery. The object we now call 3I Atlas had been hiding in plain sight for weeks, captured in images dating back to June 14th. 20 separate observations sat in computer databases, waiting for someone to connect the dots. The object had been photographed dozens of times before anyone realized what they were looking at. Why did it take so long to spot? Picture trying to find a moving star in the most crowded part of the night sky. The object was traveling directly in front of the galactic center, where millions of stars create a brilliant backdrop of cosmic confusion, like searching for a black cat in a coal mine during a power outage. The dense star fields of Sagittarius had provided perfect camouflage for this interstellar intruder. Every image showed countless points of light, making it nearly impossible for automated systems to distinguish between distant stars and this nearby visitor. The discovery algorithms kept dismissing it as background noise. Time was running out faster than anyone realized. Unlike asteroids that hang around our solar system for millions of years, interstellar objects are cosmic sprinters. They race through our neighborhood at breakneck speeds, visible for just months before disappearing forever. Miss your chance, and you'll never get another. The situation grew more urgent when astronomers calculated the viewing window. This object would remain observable from Earth only until September, when it would pass too close to the Sun to study safely. That gave the global astronomy community roughly 10 weeks to unlock the secrets of a visitor that had traveled between the stars for eons. Observatories worldwide launched into action like a coordinated emergency response. The Hubble Space Telescope cleared its schedule. The James Webb Space Telescope prepared infrared observations. Ground-based telescopes from Chile to Hawaii began round-the-clock monitoring. Every clear night became precious. The European Southern Observatory deployed their Very Large Telescope Array. 4 massive mirrors working in perfect synchronization, creating the equivalent of a single telescope 25 meters across. In Japan, the Subaru telescope joined the hunt. In Spain, the Gran Telescopio Canarias turned its 10-meter mirror toward the mysterious visitor. Even citizen scientists joined the race. The Unistellar Network, made up of hundreds of small telescopes operated by amateur astronomers, began tracking the object. Despite using instruments just 3 to 4 inches across, these dedicated observers successfully captured images by stacking multiple exposures together. The clock was ticking in more ways than one. Not only would the object soon vanish behind our sun, but its distance from Earth was constantly increasing. Every day that passed meant dimmer images and fewer photons reaching our detectors, like trying to photograph a candle that's being carried farther away every second. The astronomical community had stumbled upon a cosmic time capsule, and they had just weeks to decode its ancient secrets. What they discovered about its incredible speed would reveal clues about an unimaginably violent cosmic event that launched this visitor toward us. 7 miles of ancient ice and rock were hurtling toward our inner solar system. When the Vera Rubin Observatory analyzed their archived images, they uncovered something astronomers hadn't expected. Hidden in photographs taken on June 21st, before anyone knew to look for it, lay clear evidence of this object's true scale. The images revealed a nucleus roughly 7 miles across, making it a genuine giant among interstellar visitors. To put that in perspective, imagine Manhattan Island carved out of primordial ice and rock, then hurled between the stars for billions of years. The previous interstellar visitors were cosmic pebbles by comparison. Oumuamua stretched just 400 meters, about the length of 4 football fields. Borisov measured less than a mile across. This new arrival dwarfed them both. The size revelation came from careful analysis of the object's brightness and the way sunlight scattered off its surface. Like forensic investigators reconstructing a crime scene from tiny clues, astronomers used photometry to determine the dimensions of something 400 million miles away. The calculations showed a nucleus with a radius of 3.5 miles, give or take just 0.4 of a mile. Size matters in the cosmic realm, and this discovery changed everything. Larger objects retain their internal heat longer, keeping volatile compounds like water ice, carbon dioxide, and methane locked away in frozen storage for eons. A 7-mile-wide comet could preserve materials from its birth star system virtually unchanged, creating a natural time capsule of ancient chemistry. The Rubin Observatory had captured these crucial images using what astronomers call the legacy survey of space and time. Over 100 separate photographs taken during a 2-week period showed the object's steady movement against background stars. The telescope's massive 3.2 billion pixel camera could detect objects a billion times fainter than what human eyes can see. But the size wasn't the only surprise hiding in those archived images. The data revealed something even more intriguing. The object was already showing signs of activity while still incredibly far from the sun. A faint coma of gas and dust surrounded the nucleus, proof that this ancient visitor was beginning to come alive. Most comets from our own solar system remain dormant until they get much closer to our star. This object was releasing material while still beyond the orbit of Jupiter, suggesting it contained highly volatile compounds that sublimate at extremely low temperatures, like a deep freeze that had been unplugged after 7 billion years of storage. The Discovery team realized they were looking at something unprecedented. Previous interstellar objects had been studied only as they raced away from our sun, already depleted of their most interesting materials. This time, astronomers were catching an ancient comet in the act of awakening, watching as billions of years of accumulated ice began transforming directly from solid to vapor. The size revelation promised even more dramatic developments, as this cosmic giant continued its approach toward the inner solar system. The real question wasn't how big it was, but how fast something this massive could possibly be moving through space. 130,000 miles per hour, and still accelerating. This ancient visitor was moving faster than anything astronomers had ever tracked in our solar system. To understand just how impossibly fast that is, imagine a bullet that could travel from New York to Los Angeles in less than 90 seconds. That's the kind of velocity we're dealing with when we talk about interstellar objects. The speed measurements came from carefully tracking the object's position against background stars over several nights. Like cosmic radar, astronomers used the Doppler effect to measure how quickly it was approaching us. The radial velocity reached 61 kilometers per second, fast enough to escape the gravitational pull of our entire galaxy if it were pointed in the right direction. This wasn't just fast for a comet. This was fast for anything. The space shuttles reached their maximum velocity at just 5 miles per second during orbit. The fastest human-made object, the Parker Solar Probe, tops out at 430,000 miles per hour when diving close to the sun. This interstellar comet was moving at nearly 1/3 that speed without any help from rocket engines or gravitational slingshots. What could accelerate a 7-mile wide chunk of ice and rock to such incredible velocities? The answer lies in one of the most violent events the universe can produce: stellar encounters. When this object was still part of another star system billions of years ago, something catastrophic happened. Perhaps two stars passed unusually close together, their combined gravitational fields acting like a cosmic catapult. Or maybe a massive planet migrated inward, disturbing the outer reaches of its system and flinging countless comets into the void. The ejection process requires precise conditions. Too little velocity, and the object never escapes its home system. Too much, and it gets torn apart by tidal forces. This visitor hit the cosmic sweet spot, receiving just enough energy to break free while remaining intact for its billion-year journey through interstellar space. As it continued approaching our sun, the gravitational acceleration would increase its speed even more. By the time it reached its closest approach in late October, it would be screaming through space at over 200,000 miles per hour, fast enough to cross the entire continental United States in just 55 seconds. The hyperbolic trajectory told astronomers this object would never slow down enough to be captured by our sun's gravity. Like a marble rolling down a curved ramp, it would sweep through our solar system once and continue into the cosmic dark forever. This was a one-time-only performance, a brief cosmic concert that would never be repeated. The speed also created technical challenges for observation. Telescopes had to track the object's rapid motion across the sky, constantly adjusting their pointing to keep it in view. Like trying to photograph a race car from the grandstands, the tracking systems worked overtime to capture clear images of this fast-moving target. These incredible velocities held clues to something even more remarkable: the object's mind-bending age. 7 billion years old. this cosmic wanderer predates our entire solar system by 3 billion years. University of Oxford astronomer Matthew Hopkins ran the calculations multiple times, hardly believing the results. Using computer simulations to trace the object's trajectory backward through galactic history, his team discovered something extraordinary. This visitor likely formed when the universe was less than half its current age, during an epoch when the Milky Way looked completely different. Think about that timeline for a moment. When this comet first condensed from the disk of gas and dust around an ancient star, Earth didn't exist. Our sun was still just a cloud of hydrogen floating in space. The entire solar system was nothing more than raw materials scattered through an unremarkable patch of the galaxy. Yet this object was already fully formed, beginning its billion-year journey through the cosmic void. The age calculation came from analyzing the object's steep trajectory through our galaxy. Unlike previous interstellar visitors that traveled roughly parallel to the galactic plane, this one approached from a sharp angle, suggesting it originated from the Milky Way's thick disk. This region contains the galaxy's oldest stellar populations, ancient suns that formed when the universe was young and metal-poor. Stars in the thick disk are typically 7 to 10 billion years old, making them senior citizens compared to our 4.6 billion-year-old sun. The planetary systems that formed around these ancient stars would have created comets from primordial materials that have remained virtually unchanged since the early universe. This visitor represents a frozen sample of chemistry from when the galaxy was still in its cosmic infancy. The implications are staggering. Every molecule of water ice in this comet condensed from vapor in another star system when the universe contained far fewer heavy elements. The carbon compounds, silicate dust, and organic molecules all formed under conditions that no longer exist anywhere in the local galaxy. This is literally a piece of the ancient cosmos, preserved in perfect condition by the cold of interstellar space. Hopkins and his team used something called the Oumuamua-Oxford model to predict the most likely origins of interstellar objects. The statistical analysis suggested a 2/3 probability that this comet is older than our solar system. Among all the interstellar visitors they could potentially discover, this one ranks as the most ancient they're likely to encounter. The age estimate also explained the object's unusual composition. Spectroscopic observations were already revealing water ice signatures, exactly what the model predicted for a comet that formed around an old metal-poor star. Ancient stellar systems produced ice-rich comets because they lacked the heavy elements needed to create rocky planets close to their stars. This wasn't just another space rock passing through our neighborhood. This was archaeological evidence from the early galaxy, a witness to cosmic events that happened when the universe was young. Every observation was like reading pages from a history book written in ice and stone. The ancient age raised an even more intriguing question. Where exactly in the galaxy had this cosmic time capsule spent the last several billion years? This visitor came from the graveyard of ancient stars, a region our species has never seen up close. The trajectory analysis revealed something unprecedented in the study of interstellar objects. While previous visitors like Oumuamua and Borisov traveled roughly parallel to the main disk of our galaxy, this comet approached from a steep angle that cuts through multiple galactic layers. Like a cosmic elevator moving between floors, it traveled from the thick disk down into our local neighborhood in the thin disk. The thick disk represents the Milky Way's ancient history made visible. Picture our galaxy as a massive cosmic sandwich. The thin disk where we live contains young metal-rich stars like our sun, formed from gas clouds enriched by previous generations of stellar explosions. Above and below this active region lies the thick disk, populated by the galaxy's senior citizens, stars that formed when the universe was young and contained far fewer heavy elements. These ancient stellar populations tell the story of galactic evolution. 7 to 10 billion years ago, when this comet likely formed, the Milky Way was a more chaotic place. Stars formed in dense clusters that have since been scattered by gravitational interactions. Massive stars lived fast and died young, enriching the interstellar medium with the first heavy elements. It was during this epoch of cosmic violence that our visitor began its journey. The steep galactic trajectory suggests this object has been wandering between stellar systems for an incredibly long time. While objects from the thin disk might encounter other stars relatively frequently, thick disk wanderers travel through much emptier regions of space. This comet may have spent billions of years in the galactic equivalent of cosmic rural areas, rarely coming close to another star system. The implications for astrobiology are fascinating. If this object formed around an ancient star, it carries information about planetary formation processes that occurred when the galaxy was chemically primitive. The water ice, organic compounds, and silicate dust all condensed under conditions that haven't existed in our local region for billions of years. University of Oxford astrophysicist Chris Lintott emphasized the significance. This represents material from a part of the galaxy we've never examined up close. Every spectroscopic measurement is like receiving a postcard from the ancient cosmos, written in the language of frozen chemistry and preserved by the cold of interstellar space. The thick disk origin also explains why this object is so much larger than previous interstellar visitors. Ancient stellar systems produced more massive comets because they formed from gas clouds with different compositions and densities. The lack of heavy elements meant more material condensed as ice rather than rock, creating the kind of giant icy bodies that could survive billion-year journeys through interstellar space. This cosmic archaeology experiment was providing insights into galactic evolution that no ground-based telescope could ever achieve. By studying the chemical composition of this ancient wanderer, astronomers were essentially analyzing a sample from the early Milky Way. The thick disk origins promised to reveal something even more remarkable: pristine water ice that had been frozen since before Earth existed. 7-billion-year-old water ice, preserved in perfect cosmic cold storage, was about to tell us secrets about alien star systems. Spectroscopic observations from the Gemini South Telescope and NASA's Infrared Telescope facility revealed something extraordinary hiding within the comet's growing coma. The light signature showed clear evidence of water ice sublimating directly from solid to vapor, creating the ghostly atmosphere surrounding this ancient visitor. This wasn't just any water ice. This was H2O that condensed around another star when the universe was half its current age. Think about the journey this water has taken. These molecules formed in the outer regions of an alien planetary system billions of years ago, then spent eons frozen in the deep cold of interstellar space. The temperature out there hovers just a few degrees above absolute zero, cold enough to preserve chemical signatures from the dawn of galactic history. Now, as our sun's heat begins to warm this cosmic ice cube, we're getting our first taste of alien chemistry. Bin Yang from Universidad Diego Portales led the spectroscopic analysis that confirmed the water ice detection. The near-infrared signatures showed absorption lines at specific wavelengths that could only come from water molecules, transitioning between energy states. Like cosmic fingerprints, these spectral features provided definitive proof that this interstellar visitor was rich in the most important compound for life as we know it. The water ice discovery had profound implications. Most interstellar objects lose their volatile compounds during the violence of ejection from their home systems. The gravitational chaos that launches comets into interstellar space often strips away the most interesting materials, leaving behind only rocky cores. This object somehow survived that process with its water ice intact, creating a natural cryogenic preservation system. The amount of water was staggering. Early estimates suggested the comet was ejecting between 0.3 and 4.2 kilograms of material every second, much of it in the form of water vapor and dust grains. That's like a cosmic garden sprinkler operating at the scale of Manhattan, releasing ancient water that had been locked away since before our solar system existed. The infrared observations also revealed something unexpected: silicate grains, roughly 10 micrometers in radius, mixed throughout the water ice. These tiny particles represented dust from the original protoplanetary disk where this comet formed. Like finding ancient pollen preserved in amber, these microscopic relics carried information about the chemical composition of an alien star system. The The detection raised tantalizing questions about the potential for even more exotic compounds. If water ice survived the billion-year journey, what else might be hiding in this cosmic time capsule? Carbon dioxide? Methane? Complex organic molecules? Each new observation promised to reveal more secrets from this ancient chemistry set. Astronomers realized they were witnessing something unprecedented: the real-time analysis of pristine materials from another star system. Every photon of light reflected from this comet's coma carried information about processes that occurred when the galaxy was young. But this water ice treasure came with a cosmic deadline that was rapidly approaching. We have just months to study 7 billion years of cosmic history before it vanishes forever. The viewing window for this ancient visitor was closing faster than astronomers had hoped. Unlike comets from our own solar system that can be observed for years as they orbit the sun, interstellar objects are cosmic sprinters. They race through our neighborhood at incredible speeds, visible for just a brief window before disappearing into the infinite dark. The timeline was brutally simple: visible through September, hidden behind the sun from October through November, then briefly reappearing in December before fading forever as it raced back toward interstellar space. That gave the global astronomy community roughly 6 months total to unlock secrets that had been traveling between stars for billions of years. The challenge intensified because of the object's trajectory. As it approached the sun throughout the summer, it would become increasingly difficult to observe from Earth. Like trying to spot a candle next to a searchlight, the overwhelming brightness of our star would soon make the comet impossible to detect with ground-based telescopes. The most frustrating part? The comet would reach its closest approach to the sun in late October, precisely when it would be hidden behind our star from Earth's perspective. This is when comets typically display their most spectacular activity, developing dramatic tails and releasing the most interesting chemical compounds. We would miss the entire show. Observatory schedules around the world were being rewritten in real time. The Hubble Space Telescope cleared its calendar for July observations. The James Webb Space Telescope prepared 2 separate viewing sessions, one in August before the comet disappeared, and another in December when it would briefly reappear on the far side of the sun. Ground-based telescopes faced their own race against time. The European Southern Observatory's Very Large Telescope Array began intensive spectroscopic monitoring. The Gran Telescopio Canarias in Spain turned its 10-meter mirror toward this cosmic target. Even the Gemini telescopes in both hemispheres joined the coordinated observation campaign. The visibility challenges meant every clear night became precious. Clouds over Chile could cost crucial observing time. Equipment malfunctions turned into astronomical emergencies. Weather forecasts became as important as orbital calculations in planning observation strategies. Amateur astronomers also joined the race. The Unistellar Network, comprising hundreds of small telescopes operated by citizen scientists worldwide, began coordinated tracking sessions. Despite using instruments just 3 to 4 inches across, these dedicated observers successfully captured images by combining multiple exposures. Their distributed approach provided continuous coverage, as Earth's rotation carried professional observatories into daylight. The December reappearance would offer one final chance. But by then, the comet would be much farther from the sun and significantly dimmer. The spectacular activity that astronomers hoped to witness would be over, leaving only the fading glow of an ancient wanderer heading home to the cosmic void. This was astronomy's equivalent of a natural disaster response, with telescopes around the world coordinating observations of a target that would never return. The pressure was enormous, but the potential rewards made every hour of observation time invaluable as we raced to decode the secrets of our solar system's most ancient visitor. This 7-mile-wide cosmic wanderer made previous interstellar visitors look like pebbles in comparison. When Oumuamua first appeared in 2017, it revolutionized our understanding of interstellar objects. This cigar-shaped visitor stretched roughly 400 meters from end to end, about the length of the Empire State Building laid on its side. Astronomers celebrated the discovery as a milestone in cosmic exploration, our first confirmed visitor from another star system. 2 years later, Borisov arrived as a more traditional comet, complete with a glowing coma and developing tail. At roughly half a mile across, it dwarfed Oumuamua and provided the first opportunity to study an active interstellar comet. The observations revealed familiar chemistry: water ice, carbon monoxide, and dust grains, similar to comets from our own solar system. Now, this new arrival made both previous visitors seem almost quaint by comparison. Picture the difference between a city bus and an aircraft carrier. Where Oumuamua could fit inside a large football stadium, this object would cover the entire downtown area of a major city. The scale difference wasn't just impressive, it was scientifically revolutionary. Size matters enormously in the world of comets. Larger objects retain their internal heat longer, keeping volatile compounds frozen in storage for eons. They also survive the violence of ejection from their home star systems more easily. Think of it like cosmic natural selection. Only the biggest, most robust objects successfully make the billion-year journey between stars. The mass difference was even more dramatic. While Oumuamua weighed roughly 30 million tons, this new visitor contained at least 1,000 times more material. That's the difference between a large building and an entire mountain. The gravitational pull of this object, while tiny by planetary standards, was still strong enough to hold together a substantial atmosphere of sublimating gases. The comparison revealed something fascinating about the frequency of interstellar visitors. If objects this large were common, we should have detected many more smaller ones by now. The fact that we're seeing such a massive interloper suggests that either giant interstellar comets are incredibly rare, or our detection methods have been missing most of the traffic passing through our solar system. The brightness difference was equally striking. Where previous interstellar objects appeared as faint points of light even in the world's largest telescopes, this visitor showed clear structure and activity from the moment of discovery. Amateur astronomers with modest equipment could actually photograph it, making this the first interstellar object accessible to citizen scientists worldwide. The three visitors also revealed an intriguing pattern in their trajectories. Each approached from a different direction and followed a unique path through our solar system. Like cosmic tourists taking different routes through the same city, they provided multiple perspectives on the structure and dynamics of interstellar space. The size comparison raised profound questions about planetary formation in other star systems. If this object represented typical debris from ancient stellar systems, what did that tell us about the processes that created planets around the galaxy's oldest stars? The answers would come from understanding the unique orbital path that brought this cosmic giant to our doorstep. This ancient visitor was following a one-way ticket through our solar system, never to return. The orbital calculations revealed something that sent shivers down astronomers' spines: an eccentricity of 6.2. In the language of celestial mechanics, this number told a story of cosmic violence and billion-year journeys. Any object with an eccentricity greater than 1 is on a hyperbolic trajectory, meaning it's moving too fast to be captured by our sun's gravity. This visitor was breaking that threshold by more than 6 times. To understand how extreme this is, consider that the most elongated comet orbits in our solar system have eccentricities just slightly less than 1. Halley's Comet, with its dramatically stretched orbit, measures 0.967. Even the previous interstellar visitors were modest by comparison. Oumuamua clocked in at 1.2, while Borisov measured 3.6. This new arrival was in a league of its own. The hyperbolic trajectory told the story of the object's cosmic journey. Like a marble rolling through a curved landscape, it had been bent by our sun's gravity, but never captured. The mathematical curve described a path that swept through our solar system once and continued into the void forever. There would be no second chances, no return visits, no opportunity for follow-up studies in future decades. The trajectory also revealed the direction of the object's origin. Tracing the path backward through space and time, astronomers could determine that it arrived from the general direction of Sagittarius, where the galactic center blazes with the light of billions of ancient stars. This wasn't just a random direction. The thick disk populations in that region contained exactly the kind of old stellar systems that could have produced this cosmic wanderer. The orbital mechanics created a unique viewing geometry for different planets in our solar system. While Earth would lose sight of the object when it passed behind the Sun, other worlds would have front-row seats to the cosmic show. Mars would get a particularly close look, with the comet passing within 0.4 astronomical units of the red planet in October. That's roughly the distance between Earth and Venus at their closest approach. The hyperbolic nature of the orbit also explained why the object was accelerating as it approached the Sun. Like a cosmic skydiver falling toward our star, it was converting gravitational potential energy into kinetic energy. The closer it got, the faster it moved, reaching maximum velocity at its closest approach before slowing again as it climbed back out of the Sun's gravitational well. Navigation specialists calculated that the object would reach a maximum speed of over 200,000 miles per hour at perihelion. That's fast enough to escape the gravitational pull of the entire solar system, which is exactly what it planned to do. After billions of years of wandering through interstellar space, this visitor would spend just months in our cosmic neighborhood before returning to the dark between stars. The trajectory analysis revealed something even more remarkable. This cosmic wanderer was already showing signs of life as it began its close encounter with our Sun. 4 astronomical units from the Sun, this ancient ice ball began to come alive for the first time in billions of years. The awakening started with a whisper of sublimating ice. Even while still beyond the orbit of Jupiter, the comet began developing a faint coma of gas and dust. This was extraordinary behavior for any comet, let alone one that had been frozen solid for geological ages. Most comets from our own solar system remain dormant until they get much closer to our star, typically inside the orbit of Mars. David Jewett and Jane Liu, using the Nordic Optical Telescope, were among the first to confirm the comet's activity on July 2nd. Their images revealed a diffuse envelope surrounding the nucleus, clear evidence that ancient ice was transforming directly from solid to vapor without ever becoming liquid. The process, called sublimation, was like watching a cosmic time-lapse of 7 billion-year-old chemistry coming back to life. The coma grew steadily as astronomers watched. High-resolution images from the Gran Telescopio Canarias showed the ghostly atmosphere expanding to roughly 26,400 by 24,700 kilometers across. Picture a cloud of ancient vapor, twice the diameter of Earth, glowing softly in reflected sunlight as it expanded into the vacuum of space. What made this awakening so remarkable was the distance at which it occurred. The comet was releasing material while receiving only 1/16th the amount of sunlight that Earth gets. The early activity suggested this object contained highly volatile compounds like carbon dioxide or carbon monoxide, substances that sublimate at much lower temperatures than water ice. Spectroscopic observations began revealing the chemical composition of this ancient exhalation. The Very Large Telescope's FORST-2 instrument captured the comet's spectrum across multiple wavelengths, searching for the telltale signatures of different molecular species. Early results showed the unmistakable fingerprints of water vapor and silicate dust grains, confirming that this truly was a comet awakening from its billion-year slumber. The dust production rates were impressive for such an early stage of activity. Astronomers estimated the comet was ejecting between 0.3 and 4.2 kilograms of material every second, creating a steady stream of ancient particles that had been locked away since the early galaxy. Like opening a time capsule that had been buried for cosmic ages, each particle carried information about conditions in another star system. The tail development was equally fascinating to observe. Ground-based telescopes detected a faint tail stretching roughly 3 arcseconds in angular length, pointing away from the Sun as expected from radiation pressure. This cosmic wind was gently pushing the oldest dust in our solar system away from its ancient source, creating a trail of breadcrumbs from another star. The awakening process promised to intensify dramatically as the comet continued its approach toward the inner solar system. The amount of solar energy striking its surface would increase by the square of the decreasing distance, potentially triggering spectacular outgassing events that could make this visitor visible to the naked eye. But the chemical secrets hiding within this ancient ice would require much more sophisticated analysis to decode. Every photon of light reflected from this cosmic wanderer carried messages written in the language of ancient chemistry. The spectroscopic investigation began immediately after the comet's discovery, with telescopes around the world turning their most sensitive instruments toward this messenger from the early galaxy. Spectroscopy works like cosmic forensics, analyzing the way different molecules absorb and emit specific wavelengths of light. Each chemical compound has its own unique fingerprint, allowing astronomers to identify materials across billions of miles of empty space. The X-Shooter instrument at the European Southern Observatory's Very Large Telescope provided the first detailed spectrum, covering wavelengths from 300 to 2500 nanometers. This incredibly broad range allowed astronomers to search for signatures from dozens of different molecular species simultaneously. Like reading a cosmic library written in light, each absorption line told part of the story about this object's ancient origins. The initial spectroscopic results revealed a fascinating puzzle. In visible wavelengths, the comet's spectrum appeared remarkably featureless, resembling what astronomers call D-type asteroids. These dark, carbon-rich objects typically show very few absorption features, making them notoriously difficult to analyze. The similarity suggested this interstellar visitor might have a composition unlike anything in our local solar system. Near-infrared observations provided much more detail. The SPECS instrument on NASA's Infrared Telescope facility detected clear evidence of water ice features in the comet's growing coma. The spectral signatures appeared at exactly the wavelengths predicted for water molecules, sublimating in the vacuum of space. This was direct proof that 7-billion-year-old ice was transforming into vapor before their eyes. The Gemini South Telescope's near-infrared spectroscopy revealed an even more intriguing finding. Silicate grains, roughly 10 micrometers in radius, mixed throughout the water ice. These microscopic particles represented dust from the original protoplanetary disk where this comet formed billions of years ago. Like finding ancient pollen preserved in cosmic amber, these tiny relics carried information about stellar formation processes that occurred when the galaxy was young. What the spectra didn't show was equally important. Despite intensive searches, astronomers found no clear signatures of hydroxyl radicals or cyanide compounds, molecules that are commonly detected in comets from our own solar system. This absence suggested either different formation conditions in the ancient star system where this object originated, or unique preservation processes during its billion-year journey through interstellar space. The spectroscopic analysis also revealed subtle clues about the comet's internal structure. The way different compounds appeared and disappeared as material sublimated from the surface suggested a layered composition, with more volatile substances concentrated in specific regions. This heterogeneous structure told a story about the original accretion process in an alien planetary system. Future observations with the James Webb Space Telescope promise to reveal even more exotic compounds. The infrared capabilities of this space-based observatory could detect carbon monoxide, carbon dioxide, methane, and complex organic molecules that ground-based telescopes might miss. The spectroscopic secrets were providing an unprecedented glimpse into chemistry from the early galaxy. But the comet's journey through our solar system would soon bring it close to another world that might get an even better view. In October, this 7-billion-year-old wanderer would pass closer to Mars than most spacecraft ever get to Earth. The orbital calculations revealed something that made planetary scientists around the world take notice. While the comet would remain frustratingly far from Earth, never approaching closer than 150 million miles, it would sweep within just 0.4 astronomical units of Mars. That's roughly 37 million miles. Closer than most interplanetary missions ever get to their targets. The Mars encounter represented a unique scientific opportunity. While Earth-based telescopes would lose sight of the comet when it passed behind the Sun, spacecraft orbiting the red planet would have front-row seats to the cosmic show. The timing couldn't have been more perfect for robotic observers already stationed in the Martian system. The Mars Reconnaissance Orbiter, with its powerful cameras and spectrometers, would be positioned to observe the interstellar visitor during its closest approach. The orbiter's high-resolution imaging science experiment could potentially capture detailed images of the comet's nucleus and coma structure. Even more exciting, the infrared spectrometer might detect chemical signatures invisible to Earth-based telescopes. Marshall Eubanks, a physicist and radio astronomer, calculated the viewing geometry and found that several Mars missions could contribute valuable observations. The close approach would occur when the comet was still actively sublimating material, potentially displaying a spectacular tail and coma invisible from Earth due to our Sun's overwhelming glare. The encounter geometry also meant that Mars would experience something unprecedented, a close flyby of material that originated in another star system. While the comet would pass safely by without any chance of impact, particles from its tail might actually enter the Martian atmosphere. These microscopic fragments, traveling at interstellar velocities, could create unique meteor displays visible to robotic observers on the surface. The European Space Agency's Mars Express orbiter, still operational after more than 20 years in Martian orbit, could provide additional observations. Its suite of instruments included spectrometers capable of analyzing the chemical composition of the comet's coma and tail. The data would complement observations from Earth, providing a three-dimensional view of this ancient visitor's structure and activity. The Perseverance rover, exploring Jezero crater on the Martian surface, might even be able to photograph the comet with its camera systems. While the rover's instruments were designed for geology rather than astronomy, the close approach could make the comet bright enough to capture with long-exposure images. The timing of the Mars encounter raised intriguing possibilities for future mission planning. If this interstellar visitor proved to be as scientifically valuable as astronomers hoped, the close approach to Mars demonstrated that robotic missions could potentially intercept similar objects. The European Space Agency's upcoming missions to Mars could be equipped with instruments specifically designed to study interstellar visitors. The Mars encounter would occur at the exact moment when the comet was most active, heated by its closest approach to the Sun and releasing ancient materials at maximum rates. But from Earth's perspective, this cosmic fireworks show would be completely hidden behind our star's overwhelming brilliance. For 2 crucial months, our star would become the ultimate cosmic curtain, hiding the greatest show in the solar system. The timing was astronomically frustrating. Just as this ancient visitor reached its closest approach to the Sun and began its most spectacular display of activity, it would disappear completely from Earth's view. Like trying to watch fireworks through a searchlight, the overwhelming brightness of our star would make observation impossible from our planet. The phenomenon occurs because of the comet's trajectory relative to Earth's position in space. As the object swept through its perihelion passage in late October, it would be positioned almost directly behind the Sun as seen from our world. The angular separation would be just a few degrees, placing it well within the zone where solar glare makes astronomical observation impossible. This cosmic game of hide-and-seek represented one of the most maddening aspects of studying interstellar visitors. The period when comets typically display their most dramatic activity, developing spectacular tails and releasing exotic compounds, would be completely invisible to the majority of Earth's telescopes. Ground-based observatories would be reduced to waiting helplessly while the cosmic show played out beyond their view. The solar interference zone extends roughly 8 degrees around our star, creating a substantial blind spot in the sky. Any object passing through this region becomes impossible to observe with traditional telescopes, no matter how large or bright it might be. The scattered sunlight in Earth's atmosphere creates an overwhelming background that drowns out even the most active comets. Space-based telescopes faced similar challenges. The Hubble Space Telescope, with its position above the atmosphere, still couldn't point close enough to the sun without risking damage to its sensitive instruments. The intense solar radiation and scattered light would overwhelm the detectors, potentially causing permanent harm to this irreplaceable observatory. The European Space Agency's solar orbiter, designed specifically to study our star, might catch glimpses of the comet during the hidden period. However, its instruments were optimized for solar observation rather than comet analysis. The scientific return from such observations would be limited compared to dedicated astronomical telescopes. The Parker Solar Probe, humanity's fastest spacecraft and closest solar observer, would be too far from the comet's trajectory to provide useful data. While this robotic explorer routinely ventures closer to the Sun than any previous mission, its orbit wouldn't intersect with the comet's path during the crucial perihelion passage. The hidden period would last roughly 2 months, from early October through late November. During this time, the comet would experience its maximum heating from solar radiation, potentially triggering the most dramatic outgassing events of its entire visit. Ancient compounds that had remained frozen for billions of years would sublime away into space, carrying with them irreplaceable information about chemistry from another star system. Amateur astronomers worldwide would join professional observatories in this enforced waiting period. The global community of comet hunters and astrophotographers, who had been eagerly tracking this interstellar visitor since its discovery, would be reduced to counting days until its reappearance. The solar hiding period made the December reappearance even more precious, representing humanity's final chance to study this cosmic messenger before it faded forever into interstellar space. After 2 months of cosmic silence, this ancient wanderer would emerge from behind our star for one final performance. The reappearance would occur in early December, when the comet finally moved far enough away from the sun to escape the overwhelming solar glare. Like a performer stepping back onto the stage after an intermission, this 7-billion-year-old visitor would become visible once again to Earth-based telescopes. But this curtain call would be dramatically different from the opening act. By December, the comet would be racing away from the sun at tremendous speed, already cooling as the distance increased. The spectacular activity that occurred during its hidden perihelion passage would be winding down, like watching the final embers of a cosmic campfire slowly fade. The opportunity to study this object at peak activity would be lost forever. The viewing conditions would be challenging in multiple ways. First, the comet would appear in the morning sky, requiring observations before dawn when atmospheric conditions are often less stable. Professional observatories would need to adjust their schedules to accommodate early morning observing sessions, competing with the approaching sunrise for precious observation time. Second, the object would be significantly dimmer than during its initial discovery period. The combination of increasing distance from both the Sun and Earth would reduce its apparent brightness by several magnitudes. Telescopes that easily captured it in July would struggle to detect it in December. Only the largest ground-based observatories and most sensitive space telescopes would be able to continue meaningful observations. The comet's position near Venus in the morning sky would create both opportunities and challenges. While Venus would serve as a convenient guide star for locating the much fainter comet, the planet's overwhelming brightness could interfere with sensitive photometric measurements. Observers would need to carefully plan their observations to avoid Venus contamination while still using it as a reference point. The December observations would focus on different scientific goals than the earlier studies. With the comet now moving away from the Sun, astronomers would analyze how its activity declined and what materials remained in its coma. The cooling process would reveal information about the thermal properties of 7-billion-year-old ice and rock. Spectroscopic observations during this period might detect different compounds than those seen earlier. As the surface layers of more volatile materials sublimed away during the hidden perihelion passage, deeper, more refractory compounds might become visible. Like archaeological layers in an ancient site, different depths of the comet would tell different stories about its formation and history. The reappearance would also provide crucial data for refining the comet's orbital elements. Precise position measurements in December would allow astronomers to calculate its departure trajectory with unprecedented accuracy. These calculations would predict exactly when and where the comet would cross back into interstellar space, marking the end of its brief visit to our solar system. For many amateur astronomers, the December reappearance would represent their only chance to photograph this interstellar visitor. The summer discovery period had favored southern hemisphere observers, but the winter morning sky would be accessible to dedicated astrophotographers worldwide. This final viewing window would last only a few weeks before the comet faded below the detection limits of most telescopes, beginning its permanent journey back to the cosmic void. Every major observatory on Earth united in the greatest coordinated astronomical campaign in modern history. The discovery of this interstellar visitor triggered an unprecedented level of international cooperation among the world's premier telescopes. Like a cosmic emergency response, observatories from Chile to Hawaii immediately began sharing data, coordinating schedules, and pooling resources to maximize the scientific return from this once-in-a-lifetime opportunity. The European Southern Observatory deployed their entire arsenal of instruments in Chile's Atacama Desert. The Very Large Telescope Array, consisting of four 8.2-meter mirrors, worked in perfect synchronization to capture high-resolution spectra and images. The ALMA Radio Telescope Array, with its 66 precision antennas, searched for molecular emissions from the comet's coma. The extremely large telescope, still under construction, paused its testing program to contribute early observations. In Hawaii, the twin Keck telescopes on Mauna Kea joined forces with the Subaru Telescope and Canada-France-Hawaii Telescope. Each night, these giants would pass the observational baton as Earth's rotation carried them into daylight, ensuring continuous coverage of this rapidly moving target. The Gemini North Telescope added its 8.1-meter mirror to the coordinated campaign. The international cooperation extended beyond just hardware sharing. Astronomers from dozens of countries formed impromptu research teams, combining expertise in cometary science, spectroscopy, orbital mechanics, and galactic astronomy. Graduate students found themselves working alongside Nobel laureates, all united by the shared excitement of studying humanity's most ancient cosmic visitor. Real-time data sharing became the norm rather than the exception. Observations taken at one observatory would be immediately transmitted to analysis teams around the world, allowing for rapid follow-up observations at other facilities. If spectroscopic measurements at the Very Large Telescope revealed interesting molecular signatures, the information would trigger immediate observations at complementary facilities within hours. The coordination challenges were immense. Different telescopes operated on different time zones, used different data formats, and had varying levels of sensitivity to the comet's faint light. Project managers worked around the clock to synchronize observations, ensuring that no critical information was lost due to communication delays or scheduling conflicts. Ground-based facilities also coordinated with space-based observatories to create a truly three-dimensional view of the comet. When atmospheric conditions prevented ground observations, space telescopes would continue the monitoring program. When space telescopes were unavailable due to orbital constraints, ground facilities would maintain continuous coverage. The amateur astronomy community contributed significantly to this coordinated effort. The Unistellar Network, comprising hundreds of small telescopes operated by citizen scientists, provided distributed observations that no single professional facility could match. These dedicated volunteers filled gaps in professional coverage and provided valuable long-term monitoring data. Social media platforms became coordination tools, with astronomers sharing real-time updates about weather conditions, equipment status, and preliminary results. The traditional barriers between institutions dissolved as the scientific community recognized that this interstellar visitor belonged to all of humanity. The telescope teamwork extended to data processing as well, with computational resources from multiple institutions combined to handle the massive datasets generated by continuous observation campaigns. This level of coordination was creating an observational dataset unlike anything in the history of astronomy, but the most powerful space telescope of all was about to join the investigation. The most famous telescope in history turned its legendary vision toward this messenger from the early galaxy. On July 21st, the Hubble Space Telescope captured its first images of the interstellar visitor, adding the prestige and precision of this orbital observatory to the global investigation. The images revealed a compact, active comet with a well-developed coma surrounded by the star fields of Sagittarius. For Hubble, this was just another day at the office studying the wonders of the universe. The space-based observations provided something that ground-based telescopes couldn't: a completely unobstructed view above Earth's turbulent atmosphere. While ground observatories struggled with atmospheric distortion, weather delays, and light pollution, Hubble enjoyed pristine viewing conditions 24 hours a day. The telescope's position 350 miles above Earth meant crystal-clear images, limited only by the fundamental physics of light and optics. Hubble's advanced camera for surveys began detailed imaging of the comet's coma structure, revealing subtle features invisible from the ground. The high-resolution images showed asymmetries in the dust distribution, suggesting that material was being ejected preferentially from specific regions of the nucleus. Like a cosmic weather map, these patterns revealed information about the comet's rotation and internal structure. The Wide-Field Camera 3 prepared for ultraviolet spectroscopy sessions scheduled for November. When the comet would emerge from behind the sun, UV observations could detect hydroxyl radicals, carbon monoxide, and other molecules that emit strongly in wavelengths blocked by Earth's atmosphere. These measurements would provide crucial information about the comet's water production rate and chemical composition. The Space Telescope Imaging Spectrograph would analyze the comet's spectrum across multiple wavelengths simultaneously, creating a comprehensive chemical fingerprint of this ancient visitor. The instrument's ability to separate light into its component colors with extreme precision would reveal molecular signatures that ground-based telescopes might miss. Hubble's observations were particularly valuable because of the telescope's extensive archive of similar measurements. Over 3 decades of operation, Hubble had observed hundreds of comets from our solar system, creating a vast database for comparison. The interstellar visitor's spectrum could be directly compared to local comets, revealing similarities and differences that would illuminate the processes of planetary formation in other star systems. The telescope's scheduling committee cleared priority time for this target, recognizing its unique scientific importance. Hubble's observing schedule, normally planned months in advance, was modified in real time to accommodate this unexpected visitor. The flexibility demonstrated the astronomical community's recognition that this opportunity might not come again for decades. The imaging program would continue through the comet's reappearance in December, tracking changes in its activity level and coma structure as it cooled while receding from the sun. Time-lapse sequences would reveal the dynamics of ancient ice sublimating in the vacuum of space. Hubble's observations would also contribute to precise orbit determination, helping astronomers predict exactly when and where this visitor would exit our solar system. The telescope's ability to measure positions with incredible accuracy would refine our understanding of the gravitational forces acting on interstellar objects. The Space Telescope's investigation was complemented by an even more powerful observatory that operated in invisible wavelengths of light. The most powerful infrared telescope ever built, prepared to peer through cosmic dust and decode the chemical secrets of 7-billion-year-old ice. The James Webb Space Telescope represented humanity's ultimate weapon for studying this ancient visitor. While optical telescopes like Hubble captured beautiful images of the comet's glowing coma, Webb's infrared vision could penetrate dust clouds and detect molecular species completely invisible to human eyes. The telescope's 18 gold-plated mirror segments, working together as a single 6.5-meter collector, would focus infrared radiation from this interstellar messenger with unprecedented precision. Webb's observing plan included 2 crucial sessions, one in August before the comet disappeared behind the sun and another in December during its reappearance. The timing would allow astronomers to compare the comet's composition before and after its closest approach to our star, revealing how billions of years of accumulated ice responded to intense solar heating. The near-infrared spectrograph would be Webb's primary tool for this investigation. This instrument could detect water vapor, carbon dioxide, carbon monoxide, methane, and complex organic molecules with extraordinary sensitivity. Each compound has its own unique infrared signature, like molecular fingerprints that revealed the chemical story of this cosmic time capsule. What made Webb's observations particularly exciting was the telescope's ability to detect compounds that had never been observed in interstellar objects before. Previous visitors like Oumuamua and Borisov had been studied with less sophisticated instruments that missed many interesting molecules. Webb's unprecedented sensitivity would push the boundaries of what we could learn about alien chemistry. The mid-infrared instrument would analyze thermal emission from the comet's nucleus, providing information about its internal structure and composition. By measuring how the nucleus absorbed and re-radiated solar energy, astronomers could determine the thermal properties of 7 billion-year-old materials. This data would reveal whether ancient ice behaved differently from the relatively young frozen compounds found in our local solar system. Webb's observations would also search for isotopic signatures that could reveal information about the stellar environment where this comet formed. Different isotopes of hydrogen, carbon, and oxygen would tell stories about the nuclear processes occurring inside the ancient star that created this visitor's raw materials. Like reading a cosmic birth certificate written in atomic ratios. The telescope's coronagraphic capabilities might even allow direct imaging of the comet's nucleus, something that had never been achieved for an interstellar object. By blocking the bright light from the coma, Webb could potentially reveal surface features and rotation patterns on this 7-mile-wide chunk of ancient ice and rock. The infrared observations would complement data from ground-based telescopes and Hubble, creating the most comprehensive chemical analysis of an interstellar object ever attempted. The combined dataset would include measurements from ultraviolet through mid-infrared wavelengths, capturing nearly the entire electromagnetic spectrum reflected and emitted by this cosmic visitor. Webb's role in this investigation represented more than just another astronomical observation. The telescope was essentially performing archaeology on a galactic scale, using 21st century technology to analyze materials that predated our entire solar system. The question remained whether humanity should take the next step and actually visit this ancient wanderer with robotic spacecraft. Should humanity chase this 7-billion-year-old messenger with our fastest spacecraft before it escapes forever? The discovery of this massive interstellar visitor triggered immediate discussions about the feasibility of launching a robotic mission to intercept it. Unlike previous interstellar objects that were discovered too late for spacecraft encounters, this comet was detected early enough in its solar system passage to potentially allow a flyby mission. The window of opportunity was narrow, but it existed. Marshall Eubanks from Space Initiatives calculated multiple trajectory scenarios for existing spacecraft that might be redirected toward the comet. The analysis revealed that several robotic explorers were potentially positioned for intercept missions, though each would require significant modifications to their planned operations. The European Space Agency's JUICE mission, currently en route to Jupiter, emerged as one of the most promising candidates. The spacecraft would have an excellent view of the comet from less than 1/3 of an astronomical unit away, roughly 10 times closer than Earth's distance during the same period. JUICE's suite of scientific instruments could provide unprecedented close-up observations of an interstellar object. NASA's Psyche mission, traveling toward its namesake asteroid, represented another possibility. The spacecraft would be similarly well-positioned, approximately 0.4 astronomical units from the comet during its closest approach. However, Psyche's continuous ion propulsion system would complicate any observational program, as the engine's operation interferes with sensitive scientific measurements. The challenges were immense. Both spacecraft were designed for completely different missions and carried instruments optimized for studying metallic asteroids or icy moons rather than active comets. Reprogramming their observation sequences would require months of planning and testing. The scientific return, while valuable, would be limited compared to dedicated comet missions. Several proposed missions could be launched specifically to intercept this interstellar visitor. The study from Michigan State University examined launch windows from Earth and Mars between January 2026 and March 2026. The analysis showed that small, lightweight spacecraft might be able to reach the comet using existing rocket technology. The Janus mission, originally planned to study binary asteroids, could potentially be redirected toward this interstellar target. As a relatively small and agile spacecraft, Janus might be able to achieve the necessary velocity changes for an intercept trajectory. The mission would provide humanity's first close-up look at materials from another star system. More ambitious proposals included using gravitational assists from multiple planets to achieve the extreme velocities needed for interstellar pursuit. These complex trajectories would require decades of flight time, but could potentially follow the comet beyond the edge of our solar system, providing continuous observations as it returned to interstellar space. The cost-benefit analysis was challenging. Intercepting this interstellar visitor would require diverting resources from other planned missions or developing entirely new spacecraft on extremely short timelines. The scientific value was undeniable, but the technical and financial hurdles were enormous. Harvard's Avi Loeb went further, suggesting that NASA's Juno spacecraft could be redirected from its Jupiter mission to study the comet when it approached the giant planet in March 2026. The mission proposals sparked intense debate about whether this cosmic messenger might be more than just an ancient comet. Harvard astrophysicist Avi Loeb raised a question that sent shockwaves through the scientific community. What if this isn't natural? The controversial paper, uploaded to the preprint server in July, suggested that this interstellar visitor might be a piece of alien technology disguised as a comet. Loeb, already famous for similar claims about Oumuamua, argued that the object's unusual trajectory and properties warranted serious consideration of artificial origins. The scientific establishment reacted with everything from cautious interest to outright dismissal. Loeb's argument focused on several unusual characteristics that distinguished this visitor from previous interstellar objects. The trajectory offered various benefits to a hypothetical extraterrestrial intelligence, including relatively close approaches to Jupiter, Mars, and Venus. An alien probe could potentially deploy smaller reconnaissance devices at each of these worlds without detection from Earth-based observers. The timing was particularly suspicious in Loeb's analysis. The object would reach its closest approach to the Sun in late October, precisely when it would be hidden behind our star from Earth's perspective. This cosmic game of hide-and-seek would provide perfect cover for any activities an alien civilization might want to conduct unobserved by human telescopes. The size and speed also raised questions in the controversial paper. At 7 miles across and traveling at incredible velocities, this object was far larger and faster than typical interstellar debris. Loeb suggested that such characteristics might be consistent with a technological artifact designed for long-distance space travel rather than a natural comet ejected by gravitational interactions. The scientific community's response was swift and largely critical. Chris Lintott from the University of Oxford called the alien technology claims nonsense on stilts and an insult to the exciting work going on to understand this object. Dozens of astronomers pointed out that every observation so far indicated completely normal cometary behavior. The spectroscopic evidence strongly supported natural origins. The detection of water, ice, silicate dust, and other compounds exactly matched what would be expected from an ancient comet formed around another star. The object's coma development, tail formation, and outgassing patterns all followed well-understood physics of sublimating ice in the vacuum of space. Darrell Seligman from Michigan State University emphasized that numerous telescopic observations demonstrated classical signatures of cometary activity. The object was behaving exactly like billions of other comets throughout the galaxy, showing no evidence of artificial construction or technological capabilities. Even Loeb himself acknowledged the speculative nature of his claims, describing the paper as a pedagogical exercise rather than a definitive scientific conclusion. He repeatedly stated that the most likely explanation was completely natural, estimating the probability of alien technology at extremely low levels. The controversy highlighted the broader challenges of studying interstellar objects with limited observation time and data. The scientific method requires extraordinary evidence for extraordinary claims, and the available observations provided no such evidence for artificial origins. The alien technology debate, while scientifically unsupported, served an important purpose by focusing public attention on this remarkable discovery and emphasizing the need for more comprehensive studies of interstellar visitors. The overwhelming scientific evidence pointed toward a much more prosaic but equally fascinating explanation. This was indeed a natural comet from another star. Every piece of scientific evidence confirmed what astronomers suspected from the beginning. This was genuine 7 billion-year-old ice from another star system. The spectroscopic fingerprints told an unambiguous story of natural formation. Water ice signatures appeared at exactly the wavelengths predicted for comets, with no unusual features that might suggest artificial construction. The infrared observations revealed silicate dust grains 10 micrometers in radius, precisely matching the size distribution expected from natural sublimation processes. The coma development followed textbook physics for volatile ice heating up in sunlight. As the object approached the sun, its activity increased predictably according to well-established models of cometary outgassing. The dust production rates between 0.3 and 4.2 kilograms per second fell within normal ranges for comets of this size and composition. The chemical composition provided the strongest evidence for natural origins. Ground-based telescopes detected the same molecular species found in countless other comets: water vapor, hydroxyl radicals, and dust particles. These compounds form naturally in the cold outer regions of planetary systems, exactly where this ancient comet would have originated billions of years ago. The object's behavior during its approach to the inner solar system matched computer simulations of how primordial ice would respond to solar heating after eons of deep freeze storage. The gradual awakening of cometary activity, beginning at 4 astronomical units from the Sun, demonstrated that highly volatile compounds like carbon dioxide were sublimating at low temperatures. Thermal modeling of the nucleus revealed heat conduction properties consistent with a mixture of ice and rock. The way the object absorbed and re-radiated solar energy matched natural materials rather than any kind of engineered construction. The surface temperature variations followed patterns expected for a rotating body with heterogeneous composition. The dust tail formation provided additional confirmation of natural processes. Radiation pressure from sunlight was gently pushing microscopic particles away from the nucleus, creating the characteristic tail that points away from the sun. This phenomenon occurs automatically for any object releasing dust in the solar wind, requiring no technological intervention. The orbital mechanics also supported natural ejection from another star system. The hyperbolic trajectory with an eccentricity of 6.2 could be explained by gravitational interactions during planetary formation or stellar encounters. Computer simulations showed that such extreme orbital parameters occur naturally when massive objects disturb the outer regions of planetary systems. The age estimation provided the final piece of evidence for natural origins. If this object formed around an ancient star in the galactic thick disk, its 7 billion-year age would be completely consistent with stellar evolution models. The chemical composition predicted for such ancient systems matched the observed water-rich low metallicity characteristics. Multiple independent research teams reached the same conclusion using different analytical methods. The statistical probability of this being anything other than a natural comet was vanishingly small, approaching zero when all available evidence was considered together. The natural comet evidence was overwhelming, but the scientific value remained extraordinary. This wasn't just another space rock, it was archaeological evidence from the early galaxy, a pristine sample of materials that predated our entire solar system. The implications of studying such ancient natural materials would revolutionize our understanding of galactic evolution and planetary formation processes. This cosmic time capsule was rewriting the history books of our galaxy, one ancient molecule at a time. Studying this 7 billion-year-old visitor was like conducting archaeology on a galactic scale. Every spectroscopic measurement revealed information about stellar formation processes that occurred when the Milky Way was half its current age. The chemical signatures locked in ancient ice told stories about an epoch when the galaxy contained far fewer heavy elements and planetary formation followed different rules. The thick disk origin suggested this comet formed around a metal-poor star, one of the galaxy's early stellar generations. These ancient suns created planetary systems from primordial materials that hadn't been enriched by multiple generations of stellar explosions. The resulting comets contained higher ratios of hydrogen and helium compounds, with fewer of the rocky materials that dominate modern planetary systems. The water ice detection was particularly significant for galactic archaeology. This H2O condensed from vapor clouds around another star when the universe contained roughly half its current inventory of heavy elements. Analyzing isotopic ratios in this ancient water could reveal information about nucleosynthesis processes in early stellar generations. The silicate dust grains provided direct samples of mineral formation in primordial environments. These microscopic particles condensed from cooling gas clouds that had been enriched by just a few generations of supernovae. The composition and structure of these ancient minerals carried information about physical conditions in the early galaxy that no ground-based laboratory could reproduce. The comet's chemical composition served as a benchmark for testing models of galactic chemical evolution. Theoretical predictions about element abundances in the early Milky Way could be compared directly to measurements from this ancient visitor. Any discrepancies would require revisions to our understanding of how the galaxy evolved from its formation to the present day. The discovery also provided insights into the frequency and characteristics of planetary formation around ancient stars. If comets like this were common in early stellar systems, it suggested that water and organic compounds were abundant throughout the galaxy, even during its chemical infancy. This had profound implications for the potential emergence of life in the universe. The orbital analysis revealed information about stellar dynamics in the thick disk region. The comet's trajectory suggested it had been wandering through relatively empty regions of the galaxy for billions of years, occasionally perturbed by distant stellar encounters. This wandering history provided clues about the density and distribution of matter in interstellar space. The size and preservation state of this ancient visitor challenged models of how long-term erosion affects interstellar objects. Computer simulations had predicted that comets couldn't survive billion-year journeys through space without significant degradation. This discovery suggested that interstellar environments were less hostile than previously believed. The galactic archaeology implications extended beyond just chemistry and physics. This visitor represented a connection to cosmic history that preceded the formation of our solar system. It was a tangible link to the early universe, carrying materials that witnessed the galaxy's youth and evolution. The study of this ancient comet was opening new fields of research that combined astronomy, geology, and archaeology on cosmic scales. These insights were already changing how astronomers thought about searching for similar visitors in the future. This discovery was about to transform how we search for and study the countless interstellar wanderers that must be crossing through our solar system undetected. The successful detection and characterization of this ancient visitor proved that interstellar objects were far more common than previously believed. If astronomers could find 3 such objects within just 8 years, the actual population flowing through our solar system must number in the thousands or tens of thousands. Most were simply too small or too dark to detect with current survey programs. The discovery highlighted critical gaps in our cosmic surveillance capabilities. This massive 7-mile-wide comet was almost missed, despite being one of the largest interstellar objects we're likely to encounter. Smaller visitors, potentially carrying equally valuable scientific information, were certainly slipping past our detection networks on a regular basis. The revelation that interstellar objects could be detected early in their approach, rather than just as they departed, opened entirely new possibilities for scientific investigation. Future visitors could be studied throughout their entire solar system passage, from initial approach through perihelion and back out to interstellar space. This complete observational coverage would provide unprecedented insights into how ancient materials respond to solar heating. The success of coordinated global observations demonstrated the need for dedicated interstellar object monitoring programs. Rather than relying on chance discoveries by asteroid survey telescopes, the astronomical community was considering specialized facilities designed specifically to detect and track visitors from other star systems. The chemical analysis techniques developed for this comet would serve as templates for studying future interstellar visitors. The combination of ground-based and space-based spectroscopy, supported by rapid international coordination, had created a new standard for how such objects should be investigated. Every future discovery would benefit from these proven methodologies. The mission planning studies, even if not implemented for this particular visitor, established important precedents for future robotic encounters. The trajectory calculations and spacecraft capability assessments would accelerate response times when the next suitable target was discovered. Space agencies would be better prepared to launch intercept missions on short notice. The controversy surrounding potential artificial origins, while scientifically unfounded, highlighted the importance of thorough investigation protocols. Future discoveries would need comprehensive observational programs to quickly distinguish between natural objects and any hypothetical technological artifacts. The scientific community had learned valuable lessons about managing public interest and media attention during major discoveries. The age determination methods pioneered with this visitor would allow astronomers to place future interstellar objects in their proper historical context. Rather than just cataloging chemical compositions, researchers could now connect specific visitors to different epochs of galactic evolution. Each new discovery would add another data point to the growing picture of cosmic history. The detection of this ancient comet also validated theoretical predictions about interstellar object populations. Models suggesting that millions of comets had been ejected from planetary systems throughout galactic history were proving correct. The challenge now was developing the observational capabilities to study this vast population of cosmic wanderers. The implications extended beyond just astronomy to fields like astrobiology, planetary science, and even the search for extraterrestrial intelligence. The next generation of telescopes was already being designed with interstellar object detection as a primary capability. The Vera Rubin Observatory was about to revolutionize interstellar object discovery, potentially finding dozens of cosmic visitors every year. Located on Cerro Pachón in Chile, this revolutionary telescope was designed specifically for the kind of wide-field, high-cadence surveying that makes interstellar object detection possible. The Legacy Survey of Space and Time would photograph the entire visible sky every few nights, creating a comprehensive movie of cosmic motion that would catch even the fastest-moving interstellar visitors. The 8.4-meter primary mirror, combined with the largest digital camera ever built, would survey areas of sky that current telescopes could only dream of covering. The 3.2 billion pixel camera could detect objects 10 million times fainter than what human eyes can see, pushing the detection threshold deep enough to spot relatively small interstellar objects at great distances. The observatory's data processing pipeline was designed to identify moving objects automatically, flagging potential interstellar candidates within hours of observation. Unlike the current system where discoveries often happen by chance, Rubin would systematically search for visitors from other star systems as part of its routine operations. Computer simulations predicted that Rubin could detect between 5 and 50 interstellar objects per year, depending on the actual population density in local space. This would transform interstellar visitor studies from rare, scrambled observational campaigns into routine astronomical research. Instead of having just 3 known objects to study, astronomers could build comprehensive databases of interstellar compositions and trajectories. The early detection capabilities would be game-changing for mission planning. Rubin's ability to spot objects while they were still beyond the orbit of Jupiter would provide months or even years of advance warning. Space agencies could develop intercept missions with proper planning time, rather than the rushed emergency responses required for current discoveries. The telescope's southern hemisphere location provided optimal coverage of the galactic center region, where this current visitor had been discovered hiding among dense star fields. Rubin's advanced software algorithms were specifically designed to distinguish moving objects from background stars in exactly these challenging observational conditions. The observatory would also track known interstellar objects for much longer periods than current telescopes, following them from initial detection through their entire solar system passage and beyond. This extended coverage would provide complete datasets showing how ancient materials evolved during their brief encounters with our Sun. The machine learning algorithms being developed for Rubin would automatically classify new discoveries, distinguishing between asteroids, comets, and interstellar objects without human intervention. The system would prioritize follow-up observations based on scientific importance, ensuring that the most interesting targets received immediate attention from other telescopes worldwide. The data from Rubin would be made publicly available in near real time, allowing astronomers worldwide to contribute to interstellar object research. This open-access approach would democratize the field, enabling researchers at smaller institutions to participate in cutting-edge discoveries. The statistical power of discovering dozens of interstellar objects would transform theoretical models of galactic evolution, planetary formation, and the structure of interstellar space. But even as we prepared for this revolution in discovery, our current ancient visitor was already beginning its permanent journey back to the cosmic void. After billions of years of wandering through interstellar space, this cosmic messenger was about to begin its journey home to the infinite dark. The departure trajectory calculations revealed the final chapter of this remarkable encounter. Following its October perihelion passage, the comet would begin climbing back out of our Sun's gravitational well, gradually slowing as it converted kinetic energy back into gravitational potential energy. Like a ball thrown upward, eventually losing speed, the ancient visitor would decelerate as it fought against our star's pull. But unlike balls thrown on Earth, this cosmic projectile would never fall back down. The hyperbolic trajectory, with its extreme eccentricity of 6.2, meant the comet possessed more than enough velocity to escape our solar system permanently. By the time it crossed the orbit of Neptune in 2027, it would still be traveling at nearly 40 kilometers per second relative to the Sun. The exit point would occur somewhere beyond the heliopause, the boundary where our Sun's influence finally yields to the pressure of interstellar space. This invisible border, roughly 100 astronomical units from the Sun, marks the edge of everything we consider part of our cosmic neighborhood. Beyond lies the true interstellar medium, where this visitor had spent most of its 7 billion year lifetime. Astronomers calculated that the comet would reach interstellar space sometime in the late 2030s, carrying with it subtle changes acquired during its brief solar encounter. The heating and outgassing experienced near the Sun would have altered its surface composition slightly, creating a thin layer of modified materials that would tell the story of its visit to any future civilizations that might encounter it. The departure angle would send the comet toward the constellation Lynx in the northern sky, a completely different direction from its arrival trajectory near Sagittarius. This deflection, caused by our Sun's gravitational influence, demonstrated how stellar encounters can alter the paths of interstellar wanderers over cosmic timescales. The final velocity calculations showed that the comet would leave our solar system traveling roughly 25 kilometers per second faster than it arrived. This gravitational acceleration, a natural consequence of falling toward and then climbing away from our Sun, would send it on a trajectory that might eventually carry it to another star system entirely. The journey to the nearest stars would take hundreds of thousands of years, assuming the comet maintained its current heading. During this incomprehensible voyage, it would return to the deep cold of interstellar space, where temperatures hover just a few degrees above absolute zero. Any remaining volatile compounds would freeze solid once again, returning the ancient visitor to its dormant state. The departure trajectory also provided crucial data for predicting where future telescopes might detect this object decades from now. The extremely large telescope, scheduled for completion in the early 2030s, might be able to track the comet well beyond the orbit of Pluto, providing unprecedented observations of how interstellar objects behave in the outer solar system. Navigation specialists noted that the comet's departure path would never again intersect with our solar system's orbital plane. This truly was a one-time encounter. never to be repeated in the lifetime of our species. The ancient messenger was already preparing to carry its cosmic secrets back into the void, leaving humanity with just memories and data from this extraordinary encounter. As this 7 billion-year-old time capsule prepares to vanish forever, what cosmic secrets will it take with it into the eternal dark? The brief encounter with this interstellar visitor raised as many questions as it answered. Despite months of intensive observations with the world's most powerful telescopes, fundamental mysteries about its composition, history, and origins remained unsolved. The comet would carry these secrets back to interstellar space, where they might remain hidden for another billion years. The most tantalizing unanswered question concerned the exact stellar system where this ancient wanderer originated. While trajectory analysis suggested it came from the thick disk region of our galaxy, pinpointing its specific birth star remained impossible. Somewhere among the hundreds of billions of stars in the Milky Way, an ancient sun had once warmed this comet as it formed in the outer reaches of an alien planetary system. The isotopic composition of its water ice could have revealed detailed information about nucleosynthesis processes in early stellar generations, but the limited observation window prevented comprehensive analysis. Future visitors might carry different isotopic signatures, allowing astronomers to trace the chemical evolution of different regions of the galaxy through time. The internal structure remained largely mysterious, despite extensive study. Did this 7-mile-wide nucleus contain pristine materials from its original formation, or had billions of years of cosmic ray bombardment and micrometeorite impacts altered its composition throughout? The thermal properties observed during solar heating provided only surface-level information about this ancient architecture. The comet's rotation period, if determined, could have revealed information about its collisional history during the violent ejection process that launched it into interstellar space. Most objects acquire spin from gravitational torques during planetary formation, but close encounters with massive planets or stellar companions can dramatically alter rotation rates. The presence of complex organic molecules remained unconfirmed despite searches with sensitive infrared spectrometers. If this ancient comet contained carbon-based compounds that formed around another star, they would provide crucial insights into the prevalence of organic chemistry throughout the galaxy. Such discoveries could revolutionize our understanding of how life's building blocks are distributed in space. The visitor also carried unanswered questions about the population of similar objects flowing through our solar system undetected. How many other ancient comets pass through our neighborhood every year? Are they all water-rich like this visitor, or do different regions of the galaxy produce interstellar objects with varying compositions? Perhaps most profound were the temporal questions this discovery raised. This comet had been wandering through space since before Earth existed, a witness to galactic evolution that spanned cosmic ages. What stellar explosions had it observed? What planetary systems had it passed? What cosmic catastrophes had shaped its long journey through the void? The legacy of this encounter would extend far beyond the scientific papers and conference presentations it generated. This visitor had demonstrated that the galaxy contains countless time capsules from its ancient past, floating through space and occasionally offering brief glimpses into cosmic history. Humanity's first detailed study of such an ancient object marked a turning point in our understanding of the universe's deep history. We were no longer limited to studying our own solar system's 4.5 billion-year timeline. The cosmos had hand-delivered a sample from its youth, reminding us that we are part of a much larger and older story. The questions this visitor carried back to interstellar space would inspire future generations of astronomers to build better telescopes, launch more ambitious missions, and continue humanity's eternal quest to understand our place in the cosmic order.